All right, continuing part 3 in chapter 14. Before we get to the resonance, I want to complete a couple of practice problems real quickly because they are actually insightful. We did not do one like this with the S substitution, and it does highlight the isolating, getting in standard form kind of thing, the 1 plus thing. So what we're dealing with here is, let's see if we can get our pen. H of S is equal to, now let's just go for the standard form because that's all this is about, is getting the transfer function into standard form. So the S is isolated. We know that one, right? That is, in this case, a pole at the origin. Remember here we're making the substitution S equals J omega. And it works backwards the other way as well, obviously. Now, we're trying to isolate and get in the form of 1 plus. So we're going to be dividing by 400 out of the bottom. And that will give us 1 plus, what, 80S over 400. So that's going to be S over 5. I'm going to move this along. Plus S squared over 400. Right? Times 400. So I just pulled that out of that side. And that is equal to, right, 10 over 400 is 1/400th over, there's our pole at the origin, and 1 plus S over 5 plus an S squared over 400. Okay. And all this is basically an exercise in factoring. And I want to go back and emphasize again that our transfer functions can be factored into the product of several individual transfer functions. And then in log terms, those end up being plotted as the sum of the logs. Okay? So in this one, we've got 3 parts. And these are, so we can indicate our H of S is equal to 20 log. And when I write it like this, I don't mean natural log. I mean base 10. That's by default. Of 1/40th. And I see I botched it up here. Take that away. All right. Plus what? The log of, plus the log 20 times, I'm sorry, same thing, 20 times the log of 1 over S, right, plus 20 times the log of all this business, 1 over, right, 1 plus S over 5 plus S squared over 400. Okay? So, here we are looking at, here we've got our constant piece. And here we've got our single pole, or a simple pole, at the origin. All right, and finally then we've got the double pole at the square root of 400. Right? All right, so now we can look at, and in all of these, the book has given you, even in the answered ones, the full breakout. But let's just examine the pieces, right? Here at the bottom is our 20 log, right? This is our 20 log of 1/40th. All right, so this has been converted into 40 with the addition of the minus sign. Okay, so that's the same as this guy is the same as 20 log of 1/40th. All right, so that's our constant down below. Then we've got the single pole at the origin, right? And the origin being right here. And this is the minus slope of 20 dB per decade, right? So in this, they've reinserted JW for S, which is fine. So there's our single pole at the origin. Okay, and over here is our double pole at the square root of 400, which is 20. And we see that here. So here we have the function breaking at omega equals 20 and breaking down. So this is the double at square root of 400. Okay? And then, as you can see right up here in this whole thing, all we're doing in a Bode plot is summing up these individual pieces. We do them piecewise. So here's one dotted line one, here's another, and here's the third. And the red line is just the sum of the three. The sum of the individual HSs, right? The sum of I of them. Okay. Here was the phase angle, right? You can track in the same way up until you get to the first breakpoint, right? You have 90 degrees. This one is going to be what at this breakpoint plus and minus 90 degrees, and I think you're going to see this better on the next problem, right? But here we are starting at minus 90 degrees, and what's this a result of? This is the pole at the origin. Okay? And then it is going to break down according to that pole. I'm sorry, there's our minus 90 degrees, yeah, from the pole at the origin. And then it's going to break off at minus, it's fixed at minus 90 degrees. Then it's going to break off at, what, 40 dB per decade. So notice now, this is going through 2 decades here, right? That point, there's a decade back here and a decade forward, right? So plus and minus a decade. And it's going to go through plus and minus 90 degrees, right? Because we have a double pole there. Okay, let's look at the next one. Now, I wanted to include this one because it really is the working backwards that we're interested in. In other words, quite often the design problem says, here's the frequency response that we want. What is the transfer function that we need to aim for? And then further in the design, we could say, if that's the transfer function I want, what is the circuit or the system that will produce it? Okay, so let's do kind of the reverse of what we just did. Take this apart piece at a time. At each breakpoint, what causes that action? So let's look at the first term. The green line shows this all begins at low frequency at something called 40 dB. All right? And that's going to represent a constant term. So what is that constant term the result of? What we know is 40 dB is equal to what? 20 log of x. So x, or we can say log of x, must equal, 40 divided by 20 must equal 2. So what? X equals 100. Okay? When we go for our function, that's going to be the magnitude function. The next thing that happens is it's going to break positive, right? So this means there's some kind of a simple zero at omega equals 5. All right, so that means in the numerator there's going to be some term. So now we have, as we put together our numerator, call it as omega, right? Our numerator is going to be 100, the constant term, times what? 1 plus j omega over 5, right? And then we'll have a denominator, I guess, unless we're not done here. So now it gets bent back down, right? So how did that happen? The denominator had to have gotten bent back down. If you'll notice right here in the pivot point, this is going to keep on going up and up and up as long as omega increases. What we need is a counterbalancing force. And here it is, coming down the other way. So we need a simple pole at 10, right? So the denominator is going to have something 1 plus j omega over 10 as one of the terms. Okay. And once this kicks in, this simple pole kicks in, it's going to counteract that simple zero, and you're going to end up with this, this horizontal line here. All right, now finally we need it to break down at twice the normal rate. So that tells us we've got a quadratic pole at 100, right? So then there has to be some term here, 1 plus, we could indicate it easily as our, let's see, we're going to want j omega squared, so it's going to be something with omega squared over, if it's at 100, it's going to be 100 squared, right? So we'll have some terms like this. Okay? Oh, now this I have to say, this is very interesting. I did this a number of times. I have no idea where they got this. This is definitely not right. So if I list this in terms of s's, here's our 100. I put 100 in here. Whoops, here's our s plus 5, where s is j omega, right? So this has been cleaned up where it's s plus 5, but then we'd factor out a 5 and we'd have 1 plus s over 5. So that's what I'm doing. That's what this term is about. Same thing is happening here. Here we need to make an adjustment. I think I've rushed to judgment here. This would be what? S squared plus 200 s plus 10 to the 4th. Right, so for me to have a simple pole here, I would really need to be looking at 1 plus omega over 100, right, squared, or j omega over 100 squared. Okay? All right, so I wanted to get those two in because this one, especially problem 6 here, is very representative of how the design problems happen in real life. Okay, now we're going to move to the subject of resonance, but as we do, one thing I want to mention that's important is there are a couple of functions, effects of transfer functions, and they occur easily in circuits, but they actually occur very generally in real life, not just in electronics or a basic or otherwise. Resonance is one of those frequency response functions, one of those very critical frequency response functions. Another one is filters. And we're going to cover both of those now, not in this section, but this in the subsequent part. But these are two very important, commonly recurring aspects of frequency response. So we're going to spend some time and make sure we get this right. Resonance, all I can say is it's in the math. It's not about electronics, once again. It's in the math. Okay? If you've never seen it, dial up the pictures of the Tacoma Narrows Bridge up in Tacoma, Washington. This was a bridge that was designed. You can see the span here. It's already got a bend and an arc in it. This is an example of the mechanical resonance being expressed in a very high, apparently rigid mechanical structure. If you've ever been to or can imagine the Tacoma Narrows, this is a bridge over a very deep gulf down here, a river and a canyon. It's just a dugout, a gorge, that's the word I'm looking for. And what happened on this particular day is the wind started blowing and it matched the built-in resonant frequency. In other words, this bridge had a frequency response. And the wind found out where is the 3 dB point, where's the break point, where's the corner frequency in that. And the result was this. It got the bridge whipping and whipping to the point where it eventually exploded, collapsed. There are some excellent videos online of pictures taken looking right down the center line from one end of the bridge to the other. And you can watch right in here, you can watch the center line stay straight and the bridge vibrate back and forth around that center line. It's very dramatic, very beautiful, but this is kind of, it's just starting to get going, and here, of course, it's exploded. We experience resonance all the time in music, that which we love. The easiest to see it illustrated in the brass. You've probably heard talked about this kind of thing where glass, this is presumably a wine glass, and if it's a high enough quality and uniform in its thickness all around, and especially if it's thin, you can hit the frequency. There is a resonant frequency. There is an omega 0 of this glass, of the glass material. And this is the pictures of the glass, 3 steps, 1, 2, and then finally collapsing, where some sound has been introduced, right, as from the French horn here, although it didn't come from that, I can assure you. But some sound came, so the energy came and matched the resonant frequency of the glass material itself. And just like the Tacoma Narrows Bridge, it shattered. Well, it's not just limited to simple, the bridge isn't a simple thing. But here's an example in a modeling sense of a large airplane. Look, a 4-engine jet airplane. I forget which model this is, doesn't matter. But just in a wind tunnel. Now, if you knew this was happening when you were a passenger on a plane like this, you would probably not like it at all. In fact, you probably don't believe this really happens in airplanes. But it does. And as you can see, like in this model, the planes can survive it. They might not survive it. This is pretty extreme. But it's a whole aeroplane experiencing resonance. Okay? So, back up here, I'm telling you, resonance is in the math. It's not about electronics. Okay. So there's 2 kinds of resonance we're going to talk about here today. Series and parallel. Series resonance, we'll spend the most time on this, and parallel is a straightforward extension of that. So it's a condition in an RLC circuit in which the capacitive and inductive reactances are equal in magnitude. In other words, you end up with an RLC circuit that behaves in a purely resistive way. Okay? In other words, the imaginary terms cancel. That's really what this is about. So here we have that RLC circuit, And we're going to analyze what? The transfer function we're interested in is impedance. So that's V over I. Simple, straightforward. That's R plus J omega L, 1 over J omega C. And this is the term we're going to want to drive to 0. So let's isolate it. Here's the resistance plus the imaginary term. And if we make this go to 0, I'll pretend that that's it. That's the condition we're aiming for. So obviously what's happening? We want to know what frequency causes this. And that frequency is, let's just set them equal to 0. And here it is in hard terms, as an omega and as a frequency. Pretty simple. So look at this. In a simple RLC circuit, we've got a frequency at which the values of L and C cause the imaginary term to just disappear. And that means the load appears, right? This whole piece goes to 0, so the load appears purely resistive. Now we also know that that will be, right, the lowest impedance, because as soon as this term becomes non-zero, whether it's plus or minus, as soon as it becomes non-zero, the magnitude of impedance is going to increase. Right? This will increase whenever this is non-zero. If it's non-zero, then Z is greater than R. Okay? All right, that's the simple case. We've now found that. All right, so let's look closely at it then. We've got the current, so we're taking apart. Remember, Z was VM over I. So now we're just taking it apart. So backing up a step and saying the current will be the voltage divided by the magnitude of Z. And so here it is, our R squared. Our terms are easy, our R squared plus this whole thing squared. Whoops. And that's going to look like this. Okay? And so here is that expression, Vm over R. This will be the peak, just like it's shown here. Here are the other two real important points. And you can guess from the Bode plot, right? These are the corners, the corner frequency. Notice the magnitude is 0.707 times that. And why is that? Right? At the corners, well, we're just defining it to be that, right? We like this because it's the half power point. Okay? So these are some important numbers that just come out. Those half power points define the bandwidth. Right? And you often hear bandwidth talked about in everything, including aerodynamics and water flow. I mean, you can imagine water flow. Look at some of the troubles they're having with dam breakings and things. That's not just too much water. I mean, once that starts flowing, you know, many of those systems never get tested until nature intervenes. All right, so here's the power. Let's talk about that. This is the average power, right, in the resonance circuit, 1/2 I squared R. We know this from many previous applications. All right, the peak power is just 1/2 Vm squared over R, right? RMS here we're talking about. So the power at the half power points is defined, right? This is defined. And it's defined as what, the RMS, this is RMS voltage, right? And if we square it and divide by 2r, we end up with this amount of power. Okay? And so this defines for us exactly where the half power points are in terms of, look, we can just solve for it. We get them plus and minus. Here we can just solve for this. We solve for omega in terms of the components, right? We solve for omega as a function of r, l, and c. And we can do that, right? It's just a matter of extracting, squaring things, and then taking the square root. As you might expect, here's our favorite quadratic, right? And as opposed to saying, remember we have the minus b plus and minus the square root for the quadratic form. Whoops, so b squared minus 4ac all over 2a, right? That standard form. Well, here we've just said we know we're going to have the plus and minus, so I'm just going to say here's going to be my base point, and the omega 1 and the omega 2 are equally spaced about the central point. Okay, so this is essentially our central point right here. Okay, so another thing that's important is the Q of the circuit. And what this is going to be about is Q is chosen for the term quality. It is defined, right? So here's something else that's just a definition. It's a sensible definition, but it's a definition nonetheless. The 2 pi, I'm not going to argue. It's really relating the peak energy stored, like in an inductor, divided by the energy dissipated in one period at resonance. Okay? So now, how might this look in real life? What would be the point of the Q? What makes one Q better than another for a circuit? Well, here we can let's put some mathematics to the definition. Here's our 2 pi. Here's our stored energy, right? 1/2 Li squared. We're used to seeing that. Here's the dissipated energy in one period. Notice it's a function only of R, right? Because at resonance, R is the effective, or essentially the seen part of the impedance. Okay? And this just averages over a period, right? All right. If we do all the math on this, cancel out the i's and the l's and blah, 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 we get 2 pi f, right? L over r, which is omega, right? 2 pi L over r. So we could do the same thing in terms of the capacitor, stored energy in the capacitor, and it would come out in this form, as you might guess. Okay? So, and by the way, if you want to, you can work this backwards. You can take these two terms and find omega 0. Whoops, find omega 0, right? And you'll get 1 over the square root of, well, LC. Okay? Easy enough. So that's our Q. What does it look like? Why? What's important about it? Peak energy versus dissipated energy. Well, here's the thing. A high quality Q means the peak is real sharp. Okay, bandwidth is narrow. This narrow bandwidth goes with this high peak, this one out here. This is the sharpest. This Q3 equals the sharpest. Okay, and why do I care? Well, this flat one here does a poor job, of separating. Or we could say discriminating. So if you were using it to tune a radio, anything that involves tuning frequency, radar, sonar, anything that involves tuning, you want this peak to be as sharp as possible. You want to discriminate as much as possible. Okay? And so that's why we pay attention to the Q, and it has a real bearing in circuit design. All right. I kind of wrote over this, but we can see here. Clearly what's happening, you got omega 1. I just rewrite omega 1. Omega 1 is approximately omega 0 minus the bandwidth over 2. That's sort of obvious, right? So those are simple relationships once you find the Q. Or in a design problem, the Q is often the thing that is put forth as a criteria. It's the demanded thing. The bandwidth can also be, this is just manipulating the numbers we've already got. The bandwidth is R over L. It's omega 0 over Q, right? And we get that simply by working this that math backwards. Okay, so let's remember some of those. And here is problem 14.7. So we got a series circuit. We'll do this. A series circuit of R, L. Calculate the value of C to produce a certain quality factor, right? So we have R equals 4. L equals 25 millihenries is equal to 0.025 henries, all right? And the first thing we want to know is we have a quality factor of Q, and we want to know exactly what's the value of C. All right, well, one thing we can find right away is what's the omega 0? We don't know that, right? But we do know that 50 then is equal to what? Omega 0 L over R. We just derived that. So we know these two things, and we can find then that omega 0 is, what have we got? 50 times 4 divided by 0.025. And this is looking like, let's see, that goes into there twice with an extra 100. So 25 or 20 times 4, this looks like about 8,000. 8,000 hertz. Okay? All right, now we can go back to our Q again and calculate it in terms of C, but now we know, right, it's 1 over omega 0 RC. We needed to get this in order to solve it. So this is equal to 1 over 8,000 times 4 times C. All right, and that's equal to 50. And when you do the math there, you get C will be equal to 1 over, I'm not going to take time for all of the cancellations and so forth, 1.6, right, times 10 to the 6th. So that looks like 1 over 1.6, that's about a 6, so 0.625, and 10 to the 6th here makes this microfarad. Okay, and I see that's what he's got down here. All right, what else do we need to find? Omega 1, omega 2, and beta. So let's see. Why don't we find, not beta, but the bandwidth. All right, so part B. The bandwidth is quite easily from our previous slide, R over L. All right, so that we could have had right away. 4 divided by 0.025 is equal to what? That's essentially 40 times this is 160. So the omegas and 2 are going to be omega 0 plus and minus half of this, b over 2. And so what have we got? We've got this thing is going to become 80. So it looks like we're looking at 8080 and what else? 8,000 minus 80 will be 7920. Okay. How does that look? Yeah, okay, that's what they're talking about here. And in order to get the order correct, the lower one is omega 1, and the higher frequency is on the up frequency side, so that's going to be that. Now, determine the average power dissipated at each of these locations when VM is 100. Okay, and I think in the interest of time, we're going to, I'll just press on with these. It's pretty easy to see the answers. Okay, so the peak power we know, the power at the peak, we derived that a couple slides ago, 1/2 VM squared. Remember, it's all R at this point. So we've got VM squared, so 100 squared over 2 times 4. So this is 10,000 divided by 8 is 1.25 kilowatts. Okay, now the power at the omega zeros, the power, the power at omega 1 and omega 2 are equal, and they are what? The half power points. That's the definition. So that means those are half of this, or 0.625 kilowatts. Okay? Okay, so let's move on to parallel resonance. Same approach. Actually, most of this we've already derived already, so that's very nice. But let's go with it here. You see the same circuit, right? What's important in finding the resonance? It's going to be same through resonance, whether it's series or parallel. The same thing is going to apply for filtering. Okay, to analyze it, we need a transfer function. Okay, the simplest one in the series case, the simplest one was z of omega. Here, pretty obviously, the simplest one is going to be y of omega. Okay, and hopefully I haven't written over. I have. Let me see if I can maybe erase some of these things. Use my pointer option and get the eraser going here. Oh, so nice. All this electronic stuff, so nice. All right, so now we have that as our chosen transfer. Whoops. I didn't change it. All right, we have that as our chosen transfer function. And all we need to do is find it. So the beauty in a parallel circuit is it's just the sum of the admittances. And so here's the one that we're going to target, which is the real. And then here's going to be the part that we're going to want to see approach 0, right? All right. So let's put them together, and we have this. Pretty straightforward, simple math. Omega c, this is looking very familiar again. Omega 0 is, what a shock, the same thing as before, right? 1 over LC, the square root of LC. And here's that picture, except for the fact that we're now looking at this as a peak value. Picture looks the same, right? We're plotting voltage. We're plotting voltage because the transfer function, remember, is I over V. But you could plot them either way. There's no argument that can be made there. All right. We can go through all the math again, but we might as well rush straight away. We've got the same or similar looking breakpoints at omega 1 and omega 2. What's been substituted now? Everything is in terms of RC, right, instead of RL. And don't you recognize how similar? Remember, 1 over RC is equal to the time constant, right? It's the time constant of an RC circuit. And if you want to look, you're going to see, and by the way, isn't that what's showing up right here as well? Okay. And if you go back and look at the ones for the series RLC, if you look at them in terms of the inductor, you'll find it's the time constant for an RL circuit. Okay. This is not a shock because all these things are basically being derived from the same fundamental ideas. Here's the bandwidth, right? Now expressed as, that time constant. Very nice. All right, let's move on to the Q now, where you've got omega 0 over beta. And beta, I keep saying beta, it's the bandwidth, right? The bandwidth, remember, is going to be, the bandwidth is going to be the center frequency. Where are we here? Whoops, the bandwidth is going to be the center frequency. So it's going to be twice this little delta here, right? And this is the delta that I'm talking about. So it's going to be twice that, which means the bandwidth is going to be 1 over RC. Okay, so let's go back to this. And we've got our omega 0 RC, bandwidth 1 over RC. And here we are right back to the same thing where it's omega 0 R over L, right? The time constant, or in this case, the inverse of the time constant. There's that RL type time constant. Okay, so omega 1 then, expressed in terms of all of this, is omega 0, the center frequency, times 1 plus 1 over 2q. So this is going to be the disturbance, the square root of that, minus the offset. This is the beta over 2. Okay, beta. Bandwidth over 2. Same thing is true on the other side. All right, the upper side you're going plus, so this is the up, and this is the lower frequency. Upper frequency. All right? Okay. So I just wanted to summarize. This table is straight out of the book, but to make the points here, I wanted to summarize this, just go through this little table, balancing or playing off, comparing, that's the word I want, the series and the parallel circuits. Notice we derived all this. The resonant frequencies are the same. Okay? And that's no shock because it's dependent on the L and C. All right. The bandwidth is the same. Okay? Bandwidth is the same. Expressed in terms of Q, the half-power frequencies are the same. Okay? And expressed in terms of the bandwidth, the Q values are the same. Right? So the treatment is the same except for the definition of the quality factor. Right? The quality factor, they are inverses. All right. So this might, when you make design choices, you may want to be looking more at the quality factor than you will the other things, because they're just going to fall in line. But if you need a very sharp circuit, you may look at your available components, other physical things, frequency, what's the range of frequencies you're going to deal with, where's your center frequency going to be, and you may want to say, how will I achieve the quality I want? Will I achieve it better with a parallel circuit or with a series circuit? Right? And that's just a question you have to ask yourself at the time of design. Okay, let's a couple of practice problems here that are always good to illustrate. This one is really pretty straightforward, kind of a plug and chug sort of thing. You have a parallel resonant circuit. Here are the R's, L's, and C's. Okay, just find all the omegas, the Q, and the beta. So omega 0, we've said this. In fact, you could use the chart from the previous slide to do put all of these in. But omega is this, so we might as well, the center frequency is this, so we might as well put in our L, which is 20 times 10 to the minus third. Isn't it sort of to be expected, by the way, times C, which is 5 times what? 10 to the minus ninth. So this is 1 over the square root of 20 times 5 is, I'm just going to call this 10 squared, that's 100, times 10 to the minus third times 10 to the minus ninth, right? So this is minus 12th plus 2, so this is 1 over the square root of 10 to the 10th, so 1 over 10 to the 5th. 10 to the minus 5th. Whoa, don't forget that. No, no, no. And so this is 10 to the 5th. Okay? So that's radians per second. Let's not forget we're dealing with omega here. All right. If we find the bandwidth or the Q, if we find, let's say, the Q, I'm not going to do omega 1 and omega 2 because it's better to find the bandwidth first. Right? So, and bandwidth is easily found as a function of Q. So let's just do that. The Q is omega 0 RC. And I was going to say it's kind of important to point out and realize that the center frequency, the peak frequency, is not a function of the resistance. It's only a function of the imaginary elements, right? It only matters when do those things cancel each other. So we should actually have been a little surprised if omega 0 was a function of anything other than L and C. The Q now, of course, is a function of R, because that's going to be exactly the height of it, and it's going to affect the bandwidth then as well. So we've got omega 0, which is 10 to the 5th, times R, which is 10 squared, yes, times the capacitance, which is 5 times 10 to the minus ninth, right? So what have we got here? We've got 5, let's see, we've got plus 5 plus 2 is plus 7 minus 9. So this looks like 5 times 10 to the minus 2. Right? So what is that? That's 0.05. All right. I'm pausing here because I had to think something strikes me as wrong. R is 100 kiloohms. So when I do this, this is my omega 0. Let me check all my values. It is not 10 squared. It is 10 squared times 10 to the third. So this is 10 to the fifth. Aha! 10 to the 5 plus 5 is 10 to the 10th times 5 times 10 to the minus 1. So this is 5 times 10. Get rid of this. And we're looking at a Q of 50. Okay? And then the bandwidth, right? Our bandwidth is going to be, quite simply, our bandwidth is omega 0 over that Q. So that is 10 to the 5th over 50. All right, so what does this equal? If we take out the, this would be 2 times 10 to the third rads per second. Okay, so the B over 2 is going to be plus and minus 1 kilorad per second, right? So that's what we're seeing here. We're seeing our 50, our 2, and here's our plus and minus 1. This is minus 1, and this is plus 1 against this. So these are slightly different numbers from the ones in your book, but obviously the problem is going to be the same. 6th edition has slightly different numbers up here for the RLs and Cs. Process is the same. Okay? Now, there is the next one that I want to hit. That's kind of interesting. The resonant frequency, find it for the circuit in the figure. Okay, so here is our figure. And notice we do not have an RLC parallel or series. We've got some mixture. Okay, so we're going to want to have a strategy, right? What's our strategy? All right. Well, what have we been doing all along? We have found resonance at what? Where we couldn't say at, we could say where the J terms equals 0. Of what? Some transfer function. Okay? That's what we need to find. So we need to pick a transfer function here whose J term we can then pursue. All right, so that's going to be our strategy. I'm going to have to erase a few things here. I just want to make this point that we do have to have our strategy before we get going. And this is a problem. I take the trouble to mention it because you can do a lot of cranking on this thing and just spend all your time cranking. So we need to decide what's the transfer function that we're going to make. The resonant frequency is at some omega in which the load's imaginary term goes to 0. Right? A couple of simple choices. We can either find the load impedance or admittance and solve it at omega. Okay? So by that I'm looking at, we're going to be looking in here, right? This is going to be where our eye is watching. What do we see? Are we going to do Z or Y? All right? Choice is yours, what you're more comfortable with. I tend to be better with Z. So I choose Z, and I'm going to say my Z total, looking in this way. My Z total is going to be the series sum of the inductive ZL plus the parallel Z of this. Okay? And then it's straightforward from there. For me, I'm going to go pursue this parallel combination. And here it is. Right? So that piece was easy, right, for the circuit values. Now here we've got two in parallel. 20, it's the product. There it is easily. The resistance times the impedance of the capacitor over the sum, 20 minus J 2000 over W. Okay, so that's the math, and you can kind of decide how nasty is this going to get. Mostly you just need to be careful. I try to help myself here by defining some constant of the denominator, right? This is a constant of the denominator. I'm defining this and knowing where I'm headed. That is, I want the denominator to do. Why do I do this? Because I want to force the denominator, force the denominator of omega to be real. That's what I want. All right. And so I know heading in, I'm going to want to end up with the conjugate of this, and here's the conjugate, right? The conjugate of that. And when I do that, this is going to be my new denominator term, right? This is going to be my D of W. And all I have to do then is remember, if I multiply top and bottom by the plus of this, I'm going to be in good shape. So here's what it's going to look like. So ZT now is, here was my original piece, J 0.05 times omega. I insert the KD. Top and bottom get multiplied by KD. Okay? To finish out over here on the right, I've got to have this term, right, which is this guy. I got to have that term times this conjugate, right? This was my conjugate. So when I do that, I will get a numerator in terms of omega in which I have the opportunity to set the numerator to 0. I now don't care what's going on in the denominator because it is not going to determine how to get rid of the imaginary terms. I made the denominator real, right? I did this to force it to be real. So then I'm only looking at the numerator terms that are going to be imaginary. And here they are. This one you recognize is the first part here. Whoops, where are we, guys? Right here. Okay. This other piece comes from my minus sign, right? My minus sign right here allows me to take it to the other side. And I'm only interested in the imaginary part of this. So once I do J times J, I'm going to get J squared. Doesn't matter. The point is that's going to be real. And I don't care about that. What I'm interested in is this guy times this. So 20 times 4 is 80 times 10 to the 4th. So it's going to be 8 times 10 to the 5th over omega. Okay, so this was I only care about the imaginary terms. All right, easy cancellation here with the J's disappear. And now I'm just processing. This is a simple equation compared to where I might have ended up. Okay? So this says, what do I get? This cancels. That'll cancel. I multiply through by W, and I get I get what? 0.05 kdw squared. So I'm going to take 0.05 and divide both sides by 0.05. So I'll end up with kdw squared. It's going to be this times this guy. And that's going to equal 16 times 10 to the 6th. Right? How do I get that? Well, if you just divide 8 by 10 to the 5th, divided by 5 times 10 squared, right? Or if you take 80 times 10 to the 4th, divided by 5 times 10 to the 2, that's going to be 16, right? I'm sorry, 10 to the minus 2, so it's going to be 16 times 10 to the 6th, and that is square root of that. I'm sorry, dividing then by kd, we're going to end up with here's my kd contribution. All right, wait. Let me be a little careful here. I'm sorry. This is going to be kd times w squared, right? So I take my kd, go way back over here. There's 400, right? Kd gave me that. And then omega squared times this. This is also from kd, so I don't look quite as silly as I started sounding. Right? These are the two terms. If I factor omega squared out of this, I get back to kd. All right. This should be relatively easy to solve now because we're just going to end up with omega squared, which is going to be 16 minus 4, so that's going to be 12 times 10 to the 6th divided by 400, right? 3 times 10 to the 4th. The square root of that is going to be the square root of 3 times 10 squared, or 100, right? So that's 173.21, or however much it goes. Okay, and that is what we see for an answer. So that's a problem that could end up quite messy if you don't get a strategy at the beginning, and then look for little substitutions you can make here and there to keep the numbers from getting all out of hand. Because this was not too bad for a KD. Okay? A KD. All right, so we'll stop here. We'll be moving on to filters next. The other really important matter to take care of with frequency response. So we've covered resonance. Filters is next. And we'll do that in part